Hi, today we're going to be looking at the frequency response of the RLC series circuit with output at C. So our circuit looks like this. We have our RLC series circuit. We want to measure the output at C, and we put a signal with many frequencies. And we calculated the transfer function in a previous video. It looks like this. So what we need to do first is calculate the magnitude and my phase of my transfer function when S is equal to j omega, because that's what we're interested in, the frequency. So we substitute first my S by j omega, so my H of j omega becomes 1 over LC over j omega squared plus R over L times j omega plus 1 over LC. And then we need to calculate the magnitude of this. So we have the magnitude of this. When I get the magnitude of the whole quotient, the magnitude of the whole quotient is the magnitude of the numerator of the magnitude of the denominator. So I calculate the magnitude of the numerator over the magnitude of the denominator, which will be minus omega squared plus R over L times j omega plus 1 over LC. So now the magnitude of complex number, in this case, this is a real number, so the magnitude of a real number is the real number. So I get it like this. And then here I need the square root of the real plus the square root of the imaginary. Now the real is this one here plus this one here. So it's minus omega squared plus 1 over LC squared plus R over L omega squared. So that would be my magnitude. And yeah, so I can calculate this magnitude for any frequency. And my phase would become, so this is my transfer function, the phase of my transfer function is, in this case, because we have a quotient, here's the quotient. The phase of a quotient is the phase of the numerator minus the phase of the denominator. So I get that it's the phase of 1 over LC minus the phase of the denominator, which is the phase of minus omega squared plus 1 over LC plus R over L omega. So let me double check. The phase magnitude, yes, and the phase like this, exactly. So so the phase is the inverse tangent of the imaginary number over the real number. And the same here is the inverse tangent of the imaginary number, which in this case, sorry, there's a j missing, of the imaginary number, which is R over L times omega, over the real number, which is minus omega squared plus 1 over LC. So this is my magnitude and my phase, and for any frequency I can calculate these numbers. Now usually we would try to analytically calculate, for instance, for 3 key points. In this case would be for very, very small frequencies that tend to 0, for omega equals omega 0, which is my resonance frequency, and for omega, for very, very large values of omega, when omega tends to infinity. Yeah, so that's what we would do. I'm not going to do it here because it tends to be long. So what we get basically is the following. The details of these calculations can be found on the script. They are available there. You can have a look at it there. And we can see that when omega tends to 0, we can maybe see it here. So that's a number here, but that's 0 here, and that's 0 here. So actually, this goes away, and this goes away, but I keep this one and this one. So my magnitude tends to 1, and my phase, and the phase of h of j omega tends to 0. Now, the problem with the phase is that on a second order system it becomes complicated to really look at it, because the tangent of 0 is the same as the tangent of 180 degrees, and yeah, it gets complicated, and then you need to know where the complex number lies in the complex plane, and yeah, it's complicated, but we will see in the graph soon that it's the case. Otherwise, you can also calculate that, plug these equations in MATLAB and get the result there. And then when omega is equal to omega 0, my magnitude 10 is equal to, where do I have that? Is, it's a real number over RC. And the phase is equal to minus 90 degrees. And when omega tends to infinity, my magnitude, we can have a look at it here quickly. So when I have here infinity, so this is a very, very large number, and this is also a very large number, and so I have a number here divided by a very, very large number, so my magnitude tends to 0, and my phase tends to minus 180 degrees. So, yeah, if we do this numerically, we can basically probe my transfer function, my magnitude and my phase in these 3 points, and I get this. Now, also, we can look at it graphically, and the response looks like this. Yeah. So this is my response, and of course, again, it depends on zeta, on our damping factor. And that's the thing. With second order systems, we don't have one response, like in the case of the RC circuit, where it's always that one response, and the only thing that changes is the cutoff frequency. In this case, my resonance frequency changes, but also my damping factor, so the actual way my response looks like changes as well. So if I have a small damping factor, or a damping factor that's less than 1, I tend to get a peak here at the resonance frequency. So at this frequency is 1 over square root of RLC. This frequency here, where the peak occurs, and for the case of zeta equals 1, where the damping factor is 1, I get this blue curve. Yeah, and if the damping factor is higher and higher, my response becomes flatter and flatter. And the same with the phase. It starts here, and for higher damping factors, it goes flat like this, and for lower damping factors, it goes sharp like this. And one important thing to note, in this case of the series circuit, we mentioned before that the damping factor is directly proportional to the resistance because of alpha. Alpha is R over 2L here. This is 2 alpha, so alpha is R over 2L, and my damping factor is alpha over omega, so my damping factor is proportional to the resistance. So I could, in principle, think, if I think of making my resistance infinitely small, yeah, in theory, I would get an infinitely small damping factor, and in theory, this peak, this resonant peak, would go up to infinity. And it doesn't matter anymore whether I have here 0 dBs and here minus 50 or whatever, because this is infinity, the rest doesn't matter, so it becomes a resonator. However, in real life, components like, if we had like, if our circuit looked like this, say, I have an inductor in series with a capacitor. In real life, this never happens because my components that I have here have parasitic resistances. So I have some resistance somewhere, and therefore my damping factor can never be 0, and therefore my resonance can never be infinity. So another thing to mention here as well, because we have a second order system, yeah, this does look like a low-pass filter, like we saw in the RC and RL circuits, yeah, but the difference is that the slope here is minus 40 dBs per decade and not a plus minus 20 dBs per decade before. For instance, if we look at this point here, yeah, at this point here we have, say, I don't know, minus 3 dBs, for instance, and then we look at the point here, that's 1 decade later, and then I have minus 43, more or less, dBs. So I went down in 1 decade by minus 40 dBs. Now, in the case, for instance, if we had a bandpass filter, or in the case of the RLC parallel circuit, where my response looks like a bandpass filter, yeah, each of the sides, so one side is minus 20 dBs, and the other side is minus 20 dBs as well, because each of the side, well, one of the reactive components is responsible for that slope on that side, and each of them adds up to 20 dBs, minus 20 dBs per decade. In this case, both of the components are basically responsible for making this slope happen, and therefore each of them gives, so to speak, minus 20 dBs per decade, and the other minus 20 dBs per decade. So we end up here having minus 40 dBs per decade because it's a second order system. So yeah, that's how the frequency response of this circuit looks like. And in the next video, we will look at the frequency response of an RLC series circuit with output at L. Thanks for watching.